In my previous lecture, I have discussed about what is an infinite series. In today's lecture, we shall learn about the convergence and divergence of infinite series and some standard results about it. So, let us start. Convergence and divergence of infinite series. Let us consider an infinite series summation n varies from 1 to infinity, which is equal to a1 plus a2 plus a3 and so on. Okay, we define a sequence as follows. S1 is a1, S2 is a1 plus a2, S3 a1 plus a2 plus a3. Continuing like this, we get Sn is a1 plus a2 plus an, that is sum of first n terms of sequence n and the sequence Sn is called sequence of partial sums of series summation n is from 1 to infinity, where Sn is called nth partial sum of series summation n. Now, see from here. You know, S1 is a1, S2 is a1 plus a2, S3 is a1 plus a2 plus a3. You see the pattern as Sn a1 plus a2 plus an. When n approaches to infinity, then the number of terms in Sn will be infinite, and in that case, Sn limit n tending to infinity, Sn will be equal to an varies from 1 to infinity. Clear? Because if the number of terms goes to infinity, these terms will be a1 plus a2 and so on up to infinity, and in that case limit n tending to infinity, Sn will be summation n varies from 1 to infinity. So it is clear, if this sequence is convergent, then this series is convergent. If it is divergent to infinity, the series is said to diverge to infinity. If it diverges to minus infinity, the series will diverge to minus infinity. If it oscillates finitely or infinitely, the series will also oscillate finitely or infinitely. It means what? That the behavior of this series summation n is exactly same as the behavior of the sequence of partial sums of summation n. So, if we want to consider the behavior of convergence or divergence of this series, we will consider the convergence or divergence of this sequence of partial sums, right? So, let us have some examples. For example, consider the series 1 plus 1 by 3 plus 1 by 3 square, 1 by 3 cube and so on. Okay. it is very clear that this is a geometric progression, and you know that the sum of first n terms of geometric progression is Sn is a into 1 minus r raised to the power n upon 1 minus r, where a is the first term, r is the common ratio, and n number of terms. So clearly, if you want to find the sum of n terms, first n terms, it will be 1 into 1 minus 1 by 3 raised to the power n upon 1 minus 1 by 3, and it is 2 by 3, 3 by 2, 1 minus 1 upon 3 raised to the power n. So this is Sn, and we know that this series summation n, if we write it as n is from 1 to infinity, this will converge if this sequence of partial sums converge, and limit n tending to infinity Sn, it is 3 by 2, 1 minus 1 upon 3 raised to the power n, limit n tending to infinity. This term will goes to 0 as n approaches to infinity, then it will be 3 by 2 into 1 minus 0, this is equal to 3 by 2. Now the clearly the sequence of partial sums Sn converges to 3 by 2, and therefore the sum of this series is also equal to 3 by 2. This is the example of a convergent series. Next, we can also consider suppose we consider the series 3, 3 square, 3 cube, and so on. This is also a geometric series, summation n is from 1 to infinity, it is 3 raised to the power n, summation n is from 1 to infinity. Here Sn is a into r raised to the power n minus 1 upon r minus 1. Again, a is the first term, r is the common ratio, and is the number of term. So this is 3 into 3 raised to the power n minus 1 upon 3 minus 1. This is 3 by 2 into 3 raised to the power n minus 1, and limit n tending to infinity Sn. This is limit n tending to infinity 3 by 2, 3 raised to the power n minus 1, which is infinity. So the sequence of partial sums diverges to infinity, and therefore this series will also diverge to infinity. So it is very clear that the summation n and the sequence Sn will both behave exactly same. Both are convergent or divergent or oscillates between finite or infinite limits. Next, there is a very important series which is geometric series. Why it is important? Geometric series is important because we can consider the behavior of geometric series on whole of the real line. Okay, let us make the real line 0. We divide into parts. 1, here it is plus infinity, here it is minus infinity, minus 1. Suppose we have the series n varies from 1 to infinity as ar square, ar cube, and so on. Clearly, first term is a, the common ratio is r. Okay. Now the convergence or divergence of this geometric series will depend upon this r, common ratio r. Okay. So we'll discuss the cases. Case 1, when this geometric series is convergent if modulus of r is less than 1, that is minus 1 less than r less than 1. First, in this case it is convergent. Second, diverges to infinity if r is greater than or equal to 1. Okay, considering is, see, -1 to 1, it is convergent. Either 1 or greater than 1, this series is divergent, diverges to infinity. Third case, when r is equal to -1, it oscillates finitely. And case 4, when r is less than -1, oscillates infinitely. So all of the real line is covered. See, -1 to 1, equal to 1, greater than 1, equal to -1, and less than -1. So we can consider the behavior of geometric series on whole of the real line. There will be 4 cases. Modulus r less than 1, that is -1 less than r less than 1. The series is convergent. Diverges to infinity if r is greater than equal to 1. R is equal to -1, oscillates finitely, and r less than -1 oscillates infinitely. Here obviously A is considered as positive. Okay, so we'll discuss these cases one by one. So first we'll consider the case when modulus of r is less than 1. So case 1, AR square and so on. Case 1, if modulus of r is less than 1, we know that if modulus of r is less than 1, then limit n tending to infinity r raised to the power n, it will be 0. Okay, because modulus of r is less than 1, as we raise the power, then the number goes on decreasing and decreases to 0. This is the result, which is standard result of the sequence. Okay, now we consider Sn. As modulus of r is less than 1, then Sn will be a into 1 minus r raised to the power n upon 1 minus r. Limit n tending to infinity Sn is limit n tending to infinity this, and you know this r raised to the power n will tend towards 0. So the limit is a upon 1 minus r, which is a unique real number. So this is finite, and it implies limit n tending to infinity Sn is finite, and therefore summation n varies from 1 to infinity is finite, and therefore in this case this is convergent. Okay, next we consider case 2, when r is greater than 1 and r is equal to 1. Case 2, if r is greater than 1 or r is equal to r greater than 1, in this case Sn will be a into r raised to the power n minus 1 upon r minus 1. Clearly, if r is greater than 1, then r raised to the power n, limit n tending to infinity, this will be infinity, and therefore limit n tending to infinity Sn will be infinity. So the sequence Sn diverges to infinity, and therefore summation en, that is this series, also diverges to infinity. And if r is equal to 1, then in this case Sn will be a plus a n times, put r is equal to 1, a n times, this is n into a, and so limit n tending to infinity Sn, it will be limit n tending to infinity n into a, and this will again infinity. So case 2, when r is greater than 1 or r is equal to 1, this Sn diverges to infinity, and therefore summation n, that is this series, will also diverges to infinity. Okay, let us consider case 3. Case 3. If r is minus 1. Okay, if r is equal to minus 1, then the series will be summation n will be a minus a plus a minus a and so on. And in that case, Sn will be a minus a plus a minus a up to n terms, and this is equal to 0 if n is even. Okay, because 2 terms sum is 0, 4 terms sum is again 0, 6 terms the sum is 0, and this is equal to a if n is odd. So Sn oscillates between 0 and a. Okay, as Sn oscillates between 0 and a, the series summation n will oscillate between 0 and a. That means oscillates between finite limits, and therefore the sum of this series is oscillatory. Then this sequence Sn is oscillatory, and therefore this series will oscillate finitely. Next, the last, if r is less than minus 1. When r is less than minus 1, it implies minus r is greater than 1. Okay, let us put minus r as any number, say x. So clearly x is greater than 1, and in that case limit n tending to infinity, again x raised to the power n will be infinity. Now again consider Sn. It is a into 1 minus r raised to the power n upon 1 minus r, and this is equal to 1 minus r raised to the power n upon 1 minus r. It depends upon n is odd or even. If n is odd, it will be you can write it as a into 1 minus x raised to the power n upon 1 plus x. Okay, and so if n is even, it will be x raised to the power n. So it is a into 1 minus x raised to the power n upon 1 plus x if n is even, and a into 1 plus x raised to the power n upon 1 plus x if n is odd. Okay, now clearly this limit n tending to infinity x raised to the power n is infinity. So infinity, this is a finite quantity, a into 1 plus x. So this will be minus infinity if n is even, and it is clearly this is infinity if n is odd. So again it is very clear, the sequence Sn oscillates between infinite limits, minus infinity plus infinity, minus infinity plus infinity. So series summation n will also oscillate between infinite limits. So we have considered 4 cases. Case 1, when modulus of r is less than 1, what we get? The series summation n, which is geometric series, is always convergent. R greater than 1 or equal to 1 diverges to plus infinity. R is equal to minus 1 oscillates between finite limits, so we say that oscillates finitely, and R less than minus 1 oscillates infinitely. This is the behavior of a very important series, geometric series, and this series will be used in various comparison tests. So this is important. You have to learn just 4 cases: less than 1, greater than equal to 1, equal to minus 1, and less than minus 1. Okay, thank you.